Yeah, thank you very much. Thank you for a nice intro. So, and thank you for saying Tenderly is a really useful tool. And yeah, today the goal for this workshop is to, like there are two goals. One of them is to show Tenderly in action, several things, but the other goal is also to just get a broad overview of what's in there and what builders can use Tenderly for. So now I will download a lot of information and just run through all of this. And this is the overview of the platform. So just to get like the rough understanding of what's in there, and then we're gonna focus on some of the things in here. So I'll be running fast now, and if you have any questions, just type them in the just type them out or interrupt me or whatever to just focus in on what's important for you guys. So to explore what Tenderly has, well, the first thing, and this is something that we'll dive in deep today, yeah, that's virtual testnets. So it's similar to public testnet, but it's virtually a public testnet. The trick is that these are, let's say, cloud managed instances of EVM compatible networks, blockchains, that actually have an unlimited faucet, and they have something that's not visible here. They also have access to the mainnet data, so you can pick the mainnet of any network we support, almost any, and then you pretty much get it. You pretty much get all the information available on the main blockchain. And we'll see why that might be useful later. And this thing comes with a special admin RPC or cheat codes. It's also coming with a debugger, with the gas profiler, with the simulator UI. So like a nice user interface that can help you debug contracts and transactions. So that's in there. And of course, there's contract verification, the biggest evil of, of our space. That's handled as well. And we'll see more of that in detail later. So this is something that people can use for various use cases. One of them would be like I'm in a team, I'm in a DAO that's sort of has greater degree of separation. So I can actually use a testnet to deploy contracts and then hand it over to people who build the UI or the backend or subgraphs and stuff like that, and they could use it in a much more isolated way. Now, this is something that goes to the development phase, but also comes in the security research phase, and it's very useful for security researchers. But then, when you're out of development phase, just building the contracts, building the UI, there's also the other bit, and that's the Developer Explorer, that helps you keep track of all the contracts that you care about, all the wallets that you care about. You get to drill down through transactions. And again, you get to debug transactions that have happened on a public mainnet or a public testnet as well, using that debugger and the simulator UI. So this is the same thing that's available in virtual testnets, just available for public networks and public contracts. So this is also something that you would use, when you need it, when something happens, when you want to debug a transaction or see a trend or whatever. But we need to also talk about how do you know when something important happens, and that's observability and monitoring. So the monitoring bit we have, yeah, this is better, I think. The monitoring bit, we have two things. One of them is alerts, which that pretty much sends you a message, let's say on Telegram or Slack, Discord, wherever. And the message says, "Hey, this transaction happened," and you can go about alerts that match a bunch of things. Let me just open this one. So from successful and failing transactions to event parameters and event-related ones to address lists, allow list and block list and stuff like that, state change and view function change. So all of that you can pretty much configure and get notified when something happens in around those parameters. So that's one way to stay in the loop with what's happening. And you can also send it over to a webhook, so you can connect your other off-chain systems with on-chain events. And that's one way to go about it. So you get signals when something happens. The other way to go about it is through Web3 actions, which are practically serverless backends for any on-chain events. So you would, what is Web3 action? You would describe, hey, I'm interested in these contracts emitting these events, and then I want a little bit of JavaScript to run. So you would supply a bit of code that responds to changes that happen on chain. So in that sense, you're automating things. Some of that can be you simply pull out some data and send a message to Discord, let's say, or you don't really want to spin up your backend and you just want to deploy it there because it can also serve as a webhook. Or you can even say, okay, let me do invariant checks every single block on my protocol, and if something goes wrong, I want to pause it. So that's the monitoring bit of Tenderly, alerts and Web3 actions. And the latter, the Web3 actions, they have the key value store, they have the secret store with them, and they have direct access to Tenderly's RPC node. And now that we mentioned that, we can go over to the RPC node. It's a node, but it's also got node extensions, which means you can build your own RPC methods to encapsulate some logic or something like that. If you don't want to spin up your, I don't know, extra backend or an API, and you don't have that much logic, and at some point you can just wrap it in a node extension, and you get your own custom RPC method. So that's one part of the node, and the second part of the node are simulation, trace, and trace RPCs. But there's a couple more RPCs that are in there, and I'm not going to mention them now while we're doing this brief overview. So this is like the RPC that you can use, and some of the benchmarks put Tenderly's RPC node really high on the public RPC even on the latency benchmarks. So it's got speed in there. And one thing that I went around is the simulation API. It's available through Node. So Node allows you to use custom Tenderly's, simulation RPC methods. And these give you the ability to see the assets that will be exchanged, the gas estimation. So basically, either if you're optimizing for the best transaction, if you want to do something and you have several options to do it with. So what's the best composition of other protocols that will yield the best results? So you can estimate that. Or if you want to add an extra layer of security, like the wallets, some of the wallets do, showing the end user, hey, if you sign this transaction, this will exactly happen. These assets will be exchanged, this values will be exchanged, and so on and so on. So simulation API is something that you can use either for like optimizing transactions or for adding an extra layer of security to the end user, as well as some sort of research. And I don't want to go into all the answers now because I want to really jump in and show some of this in action. But this would be the complete overview of the platform. So one more time: virtual testnets in development, monitoring through alerts and Web3 actions to remain in loop and react to something that's happening, and then developer explorer helping you debug all that stuff, whether on the real network or virtual testnet, and then let's say proactive security layer through simulation API or optimizing whatever you need to optimize, and of course Node RPC that allows you to do all of this stuff with the latest data. So that would be like an overview. Are there any questions or something that popped to mind as I was going through this?
I think it's
Not.
very clear.
Yeah, go ahead.
Yeah, I don't think we have
Okay.
any questions in chat, so please continue.
All right. So I'm in this other tab, and this is the Tenderly dashboard. It's a web UI, and everything that I spoke about is here in a different layout, let's say. But we're going to start with virtual testnets, because somehow that ties it all together. And I'm going to go here and say create a testnet, and you can choose from all these networks to create a testnet. So you can see that it's mainnets and the public testnet. So I'm going to hit take ZetaChain here. I'm going to name it. And here there's a bunch of things that you can configure, and I'm not going to go in detail with this now. I'm just going to hit create. We'll see these in the next example I want to first impact here. So what you can immediately do, you can use the unlimited faucet to fund an account. You can integrate this with different frameworks, Hardhat, Foundry. You can integrate it with WAGMI and VMSO, so the UI and the client libraries. And there are some examples here in the dashboard that you can use to get this a little bit. And then what you can also do is simulate and send transactions. So I'm going to go with the first, so fund account. And I'm just going to MetaMask here. And well, the MetaMask doesn't really want to play. Okay. Yeah, I'll just copy a random address from here. So when I hit this, I can either choose ETH or any ERC20 token. So if I were to paste an address of an ERC20 from ZetaChain, I could get 1,000 worth of that token. So I'm going to use just ETH or the native balance, and that was that was easy. So I got instantly this amount of ETH in my wallet on this virtual testnet. So if my MetaMask worked, you would have seen it. Let me try adding it to MetaMask. No, it doesn't really want to work. So this part we can't really see, but this is it says completed, and that was a pretty easy way to get balance or funds for trying things out. For example, security researchers use this so that they could, set up conditions of huge volumes of assets, and using that, they could build up proof of concept that an attack vector is possible. So this is pretty handy in there. But also, if you're testing a dApp or doing something, this is a super easy and super fast way to get to test ETH, and then you get the rest, let's say. And since my MetaMask is down, I'm going to head over to some code. Actually, the idea with virtual testnets is that it's a piece of infrastructure that can connect your Solidity smart contracts with your UI, with indexers and whatnot. And it's done in such a way that you don't compete for resources on public testnets. You don't have to go through faucets to get assets, to get the native balances. And you can pretty much do whatever you want. And I'm going to show you a little workflow, a possible workflow that will be using virtual testnets. And that is like in the setup where you have a smart contract developer. So in this example, we're using Scaffold ETH, so it's Hardhat. You have front end. You can also have a subgraph. And with that, how do we manage this infrastructure and deliver it to the other members of the team? And hopefully we get some ideas how to go about CI, the continuous integration bit. So I'm going to just use the virtual testnet API to create one. So yarn stage new, and I'm going to call it Zeta, and I just need to copy the chain ID. So I paste this, and pretty much instantly, there's a virtual testnet that's created here. It's this one. So it's ready. And here, there are two types of URLs, the admin RPC link and the public RPC link. The difference is some of the methods that admin RPC has that allow you far greater control. So this is, you can do practically anything. And with public, it's restricted to the standard set of RPC methods that the EVM Center has. My RPC link is here and my environment is created. So the next thing that I need to do is actually, if I have multiple environments, so you can see a bunch of these over here. I want to switch over to Zeta, and you can see the link here, and you can see an oddly looking chain ID, and I will explain this one in a bit. But the thing that we need to do now is just say, hey, I want to activate this one, Zeta. So stage, I'm going to stage activate Zeta and wait for a bit. And what did it say? Yeah, okay, that's good. I need to update that later. And now, when I did this, now I can do stuff. I can deploy contracts. I can connect the UI and do stuff with it. And yeah, before we go there, I would just like to take a moment to explain why the chain ID looks like this. So when you create a new virtual testnet, you can actually choose the chain ID that you want to use, and you can use the default one, or even better, prefix it with something and use a completely unique one. Because why? Well, if you keep the original chain ID, that opens the door for transaction replay attacks, and it's highly unlikely that that will be possible. But for complete safety, there, it's recommended to use a custom chain ID. And this is possible here. And it's also possible if you go to settings, well, not anymore, but when you create the virtual testnet, then you can choose a custom chain ID. So we got that going. And now I want to switch to the shoes of the smart contract builder. So I'm just going to run this script, actually this one, connect hardhat. So what this does, it would take the configuration that we just saw, and it's this one, and it will place it in the hardhat setup, so it's available for deployment. So if I go here, you can see a custom Tenderly config file that contains the chain configuration. So hardhat will be able to deploy there. And let's just do that. Heading back here, and it would be yarn deploy. We need to specify the network, and I'm just going to copy this name. So it's virtual ZetaChain. I'm going to hit enter. This is not breaking anything, so that's good. And you can see that there's like this crazy amount of balance, and this is made possible using the unlimited faucet RPC. So this is what you can do when you use that admin RPC. And deploying your contract, yeah, there's a couple more contracts that need deployment, and we'll wait for that. But you can see here that this was the deployment. This was another deployment. So these went through, and you can see that there are methods such as, well, this one is the only one, create token. So this was invoked from the very hardhat deployment script, and you can see pretty much how almost instantaneously they arrive, and we have a request timeout. So not everything got deployed, but you saw how deployment pretty much went, and we can see the contracts that are deployed. So I'm going to click here and go to virtual contracts, and I can see your contract, ERC20 token factory. There are 2 tokens that were created, and that's really nice. So we managed that. I'm not going to debug this one now, but it's a bummer that it didn't go through. So yeah, these are completely verified. So if you go here, you can actually see the source code of this contract, which is a default one that came with Hardhat, and you can also see everything around the ERC20 token factory contract that's inside. Just a briefly to go over how the verification happened. So this is the Hardhat config file, and you can see, yes, this is the configuration that we have, but also there's this Hardhat Tenderly npm package. So for anybody developing on Hardhat, you can use this plugin because it enables you to do automatic verifications, which means that you don't really need to do anything. The plugin will listen for deployments and automatically verify using the Tenderly's API. So that's pretty convenient. Now you can also go without verifications, skip that step, and make it. Let me just show you that from docs. So the verification with Hardhat, you can do that automatically, but you can do also the manual verification calling the verify function, which is pretty simple. You just need to give it the contract name, address, and the list of libraries that it's using, and that's the explicit verification, let's say, or manual. All right, so we have these deployed, and let's assume that this is the deployment that we wanted, even though something didn't go through. Now, what happens is, okay, the contracts are ready, and they can be used for next steps. And the next steps would be, well, let's build an UI that does that, or let's stage this dApp so somebody can test it or try it out. And for this purpose, well, first we need to connect the Next.js repository with this VNet. What happened here? Well, pretty much the same thing. There's a Tenderly config file, and there are some modifications that will use this RPC link and this chain ID, so everything gets connected there. And this is the only thing that I needed to do. And now I'm just gonna run the UI and open it up. And you can see instantly that, oh, it says no contracts found. That's odd. Just give me a second here. Let me try running it from here. Okay, this one should be there. Okay, so I will not be able to show you that part for some reason. But the thing that I could show you is actually the faucet. So you saw that there were zeros here. So I added a little button here so that when you click it, then it calls the unlimited faucet, and you would get funds. Now, one thing that might have happened here is that because this deployment didn't fully go through, I'm going to give it another go, and maybe those contracts appear in the end. And while we wait for that, I would just like to take a moment to go into the virtual testnet's admin RPC so we can actually see what is it that you can do. So there are a couple of really fun methods in that Tenderly set balance. So you give it an address, and you give it actually an array of addresses, and then an amount. So all of these wallets here would get that amount of ETH. There's also set ERC20 balance. So you would specify the token, the wallet, and the amount of that token. So you get that. Other interesting things are the EVM increase time. So you could actually set a different timestamp for the next transaction, or by increasing time, or by specifying an explicit timestamp for the next block. You can also skip through blocks, so you can say, okay, increase for 20 in hex, and the next block number will be higher. So this is something that you can't really do on public networks. So public testnets. So one option is to maintain your own infrastructure for this sort of testing, or you can use a solution such as this to just avoid the pain of maintaining more infrastructure there. What else is interesting here? There's EVM snapshot and revert, so you can actually discard a piece of history through this. And there's also a very fun one, and that's tenderly set code, which, well, you give it an address and you give it a hex, and that hex is the bytecode that will be deployed on that address. So, you can use this for contract instrumentation or stuff like that, where you probably want to keep the old behavior, but you also want to do some other stuff to, let's say, follow through the execution of those contracts. So this is the power that actually comes with the admin RPC, and I started with set balance. That this is the one, the unlimited faucet one, but you can see that there are many others in there. So we have another, yep. Okay, I'm gonna give up on this, but the important thing is that there's this. Now, another thing that's in here is also state sync. So what state sync is, it keeps track with the data from mainnet. So let's say that the TL blocks are yours that get created whenever you send a transaction. So if my contract, if my protocol, let's say, depends on oracles, state sync allows me to access the latest value that's on the mainnet. So if you need to keep track of everything that's happening on the mainnet and get access to the latest data, well, then state sync is pretty much the thing that does it. And you can see that these transparent purple ones, they're just it looks like these blocks are made as well when you send a transaction to the virtual testnet. So you don't have to deal with laggy data, and if you need a traffic shadowing, well, this is it. So there's that, and let me just see if there's another interesting thing in here. No, there's not. So that pretty much gives you an idea what you can do with testnets. Now, this didn't change, and as I said, in here you can actually debug these transactions. You can profile, use the gas profiler, and let's open this one, create token. And this over here, it's the entry to the debugger. So it gives you all the information about transaction, also the decoded input and output. It also gives you any tokens that have been transferred from here, and it gives you a pretty detailed trace overview. Now it shows loads and stores in line with the function calls. So you can see the storage location, the original value, the new value for stores, and the original value for loads. There's also logs that are present in here. So you can see logs that got emitted as the transaction executed. So that's in there, and I'll just actually, I will keep the full trace. I will remove storage because it's crowded. So this is a very simple transaction, and things get more interesting when you have a more complex one. And you can see here that one of these functions is, well, we're not sure what it is. This is just the function selector. So if I click here, Tenderly will try to, and sometimes succeeds, sometimes fails. It will try to get the information and try to decode the function name over here using a 4-byte directory that we have. Now, for this particular one, it wasn't possible, so we'll just carry on. So since this is a fairly simple transaction, and I want to step over to the debugger and the simulator themselves, I'll simply switch over to another project. And we're outside of virtual testnets now. So you can imagine the UI was built, the subgraph is there. This whole thing went through an audit, and your protocol is live. So this is the piece of the dashboard. So when that you will use to check out what's happening, debug issues, and stuff like that. So first of all, you need to list all the contracts that you're interested in. And here I got DAI, I got Uniswap Factory, swap router, and stuff like that. So this is mostly Uniswap. And when you have these contracts, well, the transactions that appear here are only transactions related for those contracts. So we're not showing everything that's happening on the chain. We're showing only the ones that that are related to your contracts. Let me just switch on the network here. And yeah, you can also see transactions in a, let's say, multi-chain setup, so you can see all the chains that you care about. Now, what I want to do is actually skip over the successful transactions and just go to the failing ones. And this is taking a bit of time. And there we go. I want to find a transaction that's happening and involving swap router. So I'm going to filter these transactions, and I'm gonna, yeah, I don't care about the function actually. I'll just filter these, and I want to find, yeah, let's say this one, too little received. So this is a failing transaction, and let's see why it failed. So I'll just hop in there, and it says, well, this is the error, too little received. Now, if we check it out in a bit more detail, we can see the input over here, and the parameters are decoded. We can see the output. And this is the line where it actually failed, and it says amount out is great, has to be greater than or equal to this parameter, or amount out minimum. And if we check out the input, we can actually see that this is that particular value. So we need to do something to this input to make this transaction go through. We need to change it so this condition becomes true. Now, how do we figure out how to change it and what to change it to? We just hop into the debugger. I click the debug button. And here you can see, let me zoom out for a bit, a bunch of things. First of all, the whole call trace is in here. There's the stack trace to this particular line. And there's some information over here that you can use. So how do we figure out what to do with this? Well, if we go to, we have two ways actually. One of them would be to see the return value of this function, exact input internal. So in the tree, it's over here. So if I go there, we can check out this lower pan over here, and we can see the contract, the caller, the input, and we can see the output. So this is the value of amount out. And this value is apparently not greater than or equal to this. So if we take this value and put it in the parameter of transaction, then this will go through. But before we do that, I want to do another thing, and that's do use the evaluate, like eval that we have in the IDEs in 2024. So I'm just gonna take these two numbers and put them into a little array and just see what happens. So this is the valid solidity code. It's a tiny snippet, but that's fine. And you can see here that amount out is for some reason 0. Oh, I know what's the reason. And this is different. So I evaluated this little expression over here, whilst the breakpoint, let's say, was on this line. So this is even before the assignment has happened. So to evaluate this particular bit, then we need to go to the line after the function invocation. So from here, and now I'm going to, well, do the same thing and we will get a number there. So if you see this is the amount out, and this is the value that we should put in the parameters to make the transaction go through. So I'll just escape it. And now we could just say, okay, let me just send the transaction with this value, or to make sure that we're doing the right thing, we can check if this is the right answer. And how do we do that? Well, we can use the simulator UI. You remember that I mentioned it. So if I click resimulate here, it will populate the simulator UI with the exact inputs, functions, the exact block number where they says executed, the transaction index, the sender, everything was taken from the transaction and filled out here. So if I go back and find this one, so this is the amount out minimum, and I'm just gonna paste the new value so we get it here. And you can see that this one changed. This UI could be a bit improved though. This is enough to evaluate whether or not this transaction will go through. But before I simulate, I would just like to run through these things for a bit. So here you can just play around and you can move the transaction at a particular point in history. So redo the transaction at a different point, or do it on the actual block it happened. You can override the block number and timestamp that the Solidity code receives through block.number, block.timestamp. You can also override states. And this means you can take a contract, and let me take die. And then you can change any of these storage slots in that contract to see what would happen if this was assigned, actually. This is pretty much when you try to do some sort of research, creating a fixture, putting the contracts in a state that's not realistic, but that doesn't matter because you want to just try something out. I'm not going to do that here. I'm just going to hit simulate transaction, and it's loading the trace, and it says the transaction succeeded. So this was the right fix. And again, you can see here on a more realistic case, the exchange of ERC20 tokens with their dollar value present in there. You can see a far more complex call trace. And again, I'm going to remove storage slot logs. And you can also see, well, all the logs done by those contracts that were involved and stuff like that. And will it work here, decode function? It did. So we managed to find in the 4-byte directory that this was actually a signature for swap. So there's that. And besides this information, what else is available here? So you have all the events that have been emitted throughout transaction execution. So you can see all of those in, let's say, one place. Then you can check out state changes. So this is showing every single storage slot that's been updated throughout execution, and it's there. And lastly, there's gas profiler. And the gas profiler, well, shows you, oh, here it is. The gas profiler shows you a flame chart of, again, the entire call trace, but in a more humanly bearable and readable way. So you can actually go through these and, yeah, let's say here, okay, yeah, transfer, this is the function that I'm sort of curious about. And I can see the exact gas it used, but also I can hop into the debugger and see how the exact place where it was invoked from. So this gives you a nice way to navigate the entire call trace without I mean, if you prefer something like that over something like this. What's most important, it gives you the exact breakdown of the gas per function, so you can figure out what are the candidates for gas optimization in there. So we went through an entire flow of picking a transaction, debugging it, debugging the inputs actually, and finding the right ones. Now, what else is possible? Actually, let me just do a brand new simulation. So this is the simulator that just does calculations for you. It saves those simulations, but they don't end up on the public chain. They don't end up on the virtual testnet either. But you can simulate stuff on both. So here we can just explore what else we can simulate. And I'm going to do a very simple example. I'm going to call the DAI contract, and I want to mint. A bit of ETH to a random address. And let me just take it here, and I'll just put a bunch of zeros. Okay, and I want to send that from this address. I took the same one, but that's really not changing anything. It's not important that these two are the same. The problem with DAI is, I mean, not the problem. The fact is, when you see the mint function, the mint function has this modifier auth, and it's checking, the auth modifier checks whether or not the caller is contained in this, where is it? Whether or not it's contained in this mapping over here, and the mapping is wards. So the address I'm using must be present in wards. And to hack this through, what I could do is actually just remove this one and simulate against modified source code, which you can completely do. So if you have a bug fix in the code that you want to verify, you can do a simulation and just, oops, not there, and simulate with that. But I'm not going to do that. So this is one option. The second option is using those overrides that I just mentioned, and we're going to do that now. I'm going to add a state override to the DAI token, and I'm not going to change the balance of it, but I am going to change the wards array, and I'm going to say, okay, this address that is the sender of this transaction is becoming a ward. So when I do that and click simulate transaction, well, it succeeded because for the time being, I was the ward of the DAI contract. And you can check when you explore the simulation in the state changes, you can see actually the state overrides over here. So this is the storage slot for that one, and this is the value that was written to that storage slot. So this is how you can play around and do things that are not correct in reality. This address is not a ward, but I made it into a ward, so that worked, which is super useful when you're doing some sort of research or when you want to test your contracts under very specific conditions. And now that we covered that one, I want to show you some methods that are in there. Yeah, and let me just pick mainnet. So the simulation thing is available in the UI, but it's also available. Through RPC. So there's Tenderly Simulated Transaction RPC that gives you decoded logs and trace and asset changes and state changes and balance changes and stuff like that. And you use it by giving it a regular transaction as a first parameter, then block number, and then you can also use add in the state overrides. So this is for example, to change the balance of an address, to change the nonce, to set a different code for a contract, and to do the state diff that we just saw. So you would have to calculate the storage slot position and then add it in here. And this is, again, in JSON, everything that that you get. There's a trace, there's the asset changes. So you can use this RPC to get, let's say, the asset changes and compare them, optimize for the best results and stuff like that. And this is how you can use the simulator outside of the dashboard and in your code, whether it's backend or front end. This is available for integration. The second bit is simulate bundle. So simulate transaction, it will take one transaction and simulate it in complete isolation. But if you have a scenario of several transactions, then you want to simulate a bundle. And you would just add an array of transaction calls. So this is the first one, the second one, the third one. And you can also add the state overrides here. So again, I'm turning somebody into a ward. So this thing over here actually represents mint, approve, transfer from sequence. So all of these transactions, they see the result of the previous transactions of the ones that happened a bit before. So when you need to simulate a sequence, simulate bundle is your friend for that. Other interesting methods that are in here, and these are all available on the public testnets, on the public RPC, but also on the virtual testnets as well. You can you can just call estimate gas to simply get the total gas used for the sequence of transactions that you put in there. You can also use the 4-byte decoding directory through RPC. So we have decoding of inputs, of errors, events, and function signatures. For example, this one. This would be, it would decode inputs to a function call of a contract, and these would be those two arguments. The best we had here was arg0, arg1, but we figured out these two are addresses. So it gives you an idea. When you see an input, you can decode it to figure out what's happening there. What else is present? Yeah, there's event signatures, function signatures, all that kind of stuff that you can decode from the function selector. And we slid into Tenderly Node, apparently. So all of this is coming together next to the standard Ethereum methods that are available by default. So you can use pretty much anything that you saw in the dashboard, you can get it through code as well. Okay, I need a sip of water. And in the meantime, does anybody have any questions? I'll take silence as a no. And to use these remaining 10 minutes in the best possible way, I would like to quickly run through the monitoring part. So alerts and Web3 actions. And let's take alerts. And I'm going to create a new one. Oh, I reached my my limit. Let me just delete this one. Okay, what? Okay, let's do this another way. Here, I definitely have it. Okay, here we go. So what we can do is create different alerts for successful or failing transactions. We can get an alert when a function is called or an event is emitted. When an event parameter has a specific value, so greater than or something. ERC20 tokens transfers, transaction value transfers. There's also allow list and block list. So this is like you can use it in conjunction with function call. So for example, if somebody outside of allow list is calling this function, that's fishy. So you can get a signal about that. Or if somebody from the block list is calling a function or just any function in the contract, you might find it fishy and get a signal that that's happening. The balance changes are in there as well. The state changes of contracts, you can subscribe to those too. And the changes to the view functions, this is like my favorite one because it goes into Solidity quite a lot. So before I attempt to create it, I just need to see if I have any contracts here. No, I don't. Let me just add die, actually swap router, and I can come back here. So let's say that we want to do an alert when an event is emitted, and I'm going to pick the target, and the target for me is, then pick it up. Sorry, just a second. Yeah, the swap router, and I'm going to select, well, let's say transfer from swap router. And now I get to pick where to send this to. So it can be email, Slack, Telegram, Discord. It can be a Web3 action, and we'll see it in a moment. It could also be a webhook. So this alert can trigger my backend, or it can go into Sentry and PagerDuty. So Sentry is there to follow the health status of your dApp, but the PagerDuty is there to give you a heart attack at 3 a.m. when something horrible is happening and you need to react. So it's the incident bit. And let me just, is my email in here? Yeah, I'll definitely skip this because we have 5 minutes left, but you can imagine how the rest would go. You would just, as the transactions happen, you would get a bunch of messages. Now, I told you that one of the options for alerts are Web3 actions, and let's hop over to those. So if alerts just give you a notification that something has happened, Web3 actions, well, they will actually run a little bit of JavaScript for you, and I'm going to go and add one. So let's say every single time a block is mined, I want to on mainnet, and let's say 2 blocks. Blocky, it's parallel, and I'm gonna hit create. So this pretty much is deploying this code so it runs whenever a new block is mined. And whenever it runs, well, it will just log the block event. Now, while we wait for this to be deployed and to see some output, let me just quickly go over through some stuff around Web3 actions. So Web3 actions, they can, as you saw it, they can run with like periodically using a cron expression, or they can run with a block event every time a block is mined, or they can even expose a webhook. So you can actually build your webhooks deployed on Tenderly if you don't want to spin up yet another API somewhere. Especially useful in the prototyping phase. And lastly, there's transaction events. So here you can listen to events happening to transactions. And how does this work? Well, you would have to use the Tenderly CLI. You would have to create a project, and then you would have to, well, fill out a YAML, of course. The YAML should contain the description. It should contain the reference to the function that you wrote. And when I say the function that you wrote, it's an npm package actually. So this is like a function in JS. And then you have your trigger, which is transaction, and you can say, yes, I want it to be mined, coming from network mainnet. If it's a failed transaction, sent to this address. For example, this is that kind of filter, or you can go and filter it through events. So when an event is emitted by this contract and the name is this transaction submission, then we should run my cool function. And my cool function is just this thing over here. And as I explained this got fully deployed. So I'm going to go over and go to execution history. Impossible that it didn't happen. It didn't. Yeah, mainnet, and let's just do that. So you can also trigger it manually to see the execution. And I'm just going to go over here. It's submitted. This is the payload. This is the block. And after waiting for a bit, these are the console logs from there. So we got the block event that was console logged in the definition itself. When I say that, I mean, yeah, this is the actual console log. So this is what you can use to automate responses to stuff happening on chain. And the important thing here is, again, secrets and storage. So storage is key value type of storage that you can access through the code through a special object called context. And you can just read and write these values. And of course, secrets, well, you can set it and then you can edit or delete it. You can't really read it any longer. And this covers the monitoring part. This covers the, what do you do when you go live? This is particularly useful, as I said, for doing stuff like creating runtime invariant checks, where you would write a function that would do a bunch of calculations against your contracts and see if any of the invariance is broken. And before that, we saw the simulator and the debugger from the transaction listing over here that lets you figure out what went wrong with a transaction to simulate under unreal conditions that are not realistic, not actual, but sort of stretched. You have that power, and you have the virtual testnets that we saw that give you all of those tools, including the simulator, including the unlimited faucet and the admin RPC that we saw. So you can build stuff with the full mainnet data availability and with all the development and debugging tools included. So that was Tenderly in an hour. I think that's a lot that we covered today. So yeah, do we have perhaps any questions here?